Somewhere beneath the seabed of southern China, in complete darkness, under enough water pressure to crush an unprotected human body in seconds, a machine the size of an 8-story building is chewing through solid rock at a pace of about 2 meters a day. It is not moving fast. It does not need to. What it is doing has never been done before at this depth, not by any country, not by any company, not once in the entire history of tunnel engineering. In April 2026, Chinese engineers completed a section of underwater tunnel that plunges 113 meters beneath the seabed, more than the height of a 30-story building, stacked underwater, underground, in total darkness. That depth alone would be impressive for any tunnel. But this is not just any tunnel. It is part of a brand new high-speed rail line, meaning trains will eventually race through this tunnel at speeds most highways can only dream of, all while sitting under pressure roughly equivalent to what a diver would feel 120 meters beneath the ocean surface. To put it plainly, this is now the deepest high-speed rail tunnel on the planet, and the engineering problems the team had to solve to get there sound less like construction and more like something out of a submarine design manual. Let's get into how they actually pulled this off.
To understand why 113 meters is such a big deal, you need to understand what happens to a tunnel project as it goes deeper. Most underwater and underground tunnels in the world are built far closer to the surface than people assume. The Marmaray Rail Tunnel beneath the Bosphorus Strait in Istanbul reaches about 60 meters. The Eurasia Tunnel, also in Istanbul, reaches around 106 meters. And for years, that was considered close to the practical limit for this kind of large-diameter rail tunnel. The reason depth is so punishing comes down to one simple force: water pressure. For every 10 meters you descend underwater, pressure increases by roughly 1 atmosphere. At 113 meters, engineers were dealing with pressure of about 11 atmospheres, more than 10 times what we experience standing at sea level. That pressure does not just push against the tunnel walls, it pushes directly against every seal, every joint, and every piece of equipment being used to dig the tunnel in the first place. At those depths, a tunnel boring machine is not just cutting through rock, it is fighting to keep water out of its own body while doing so. And if a seal fails or a cutting tool jams, fixing it becomes extraordinarily dangerous. This is exactly why, for decades, engineers around the world treated anything past 100 meters as the edge of what was realistically possible for large-scale rail tunneling.
The tool that made this project possible has a name that sounds almost modest for what it actually does: Shenjiang One. It is a Chinese-built tunnel boring machine with a cutting head 13.42 meters in diameter, roughly wide enough to fit a 4-lane highway through its cross-section. Machines like this work by slowly rotating a massive circular cutting face embedded with hardened steel and disc cutters, grinding through rock and soil while simultaneously installing concrete lining behind it to support the tunnel walls as it advances. Under normal conditions, this is already one of the most complex pieces of construction equipment on Earth. At 113 meters below the seabed, the challenge multiplies. The machine has to withstand roughly 11 atmospheres of external pressure, while its internal systems, sensors, hydraulics, and seals all continue operating normally. Engineers on this project developed 7 distinct technological innovations specifically to survive these conditions, addressing everything from sealing systems that resist extreme pressure to structural reinforcements that prevent the machine's own body from being crushed inward over months of continuous operation. Progress was slow and deliberate, about 2 meters per day, which might sound unimpressive until you remember that every single one of those meters was carved out under conditions that would instantly disable most conventional tunneling equipment.
Here is the detail that genuinely separates this project from anything built before. Every tunnel boring machine eventually needs its cutting tools replaced. Rock and soil are abrasive, and cutting discs wear down over time no matter how well they're made. Under normal conditions, replacing these tools is already a careful, technical procedure. At 113 meters underwater, with 11 atmospheres of pressure bearing down, sending a human being into the cutting chamber to swap out worn tools becomes an extremely dangerous operation, one that many engineers would consider unacceptable at this depth. So the team building Shenjiang One developed a remote maintenance system that allows the machine's cutting tools to be replaced without any person entering that high-pressure chamber at all. Robotic systems handle the tool changes directly, operated and monitored from a safe distance, removing human beings entirely from the most dangerous part of the entire operation. This single innovation may end up mattering more than the depth record itself, because it directly addresses the single biggest safety bottleneck that has limited how deep underwater tunneling has been willing to go. Depth was never just a materials problem, it was a human safety problem, and this is the part of the story that solves it.
It's worth remembering that this tunnel is not a research experiment or a one-off engineering stunt. It is a working piece of the Shenzhen Jiangmen high-speed rail line, a 116-kilometer route designed to connect two major cities inside China's Greater Bay Area, one of the most densely populated and economically significant regions on Earth. Once complete, this line is expected to cut travel time between Shenzhen and Jiangmen from roughly 2 hours down to under 1 hour. That may sound like a modest convenience, but at the scale of a region containing tens of millions of people and some of the country's largest ports, manufacturing hubs, and financial centers, shaving an hour off a regular commute or business trip translates into a genuinely significant economic effect. Faster, more reliable connections between cities in this region mean goods move faster, workers can commute across a wider area, and economic activity that used to be constrained by travel time becomes far more fluid. This tunnel is not depth for the sake of depth. It exists because the geography under the Yanjiang River estuary demanded going this deep in order to connect these two specific cities in the most direct way possible. It's worth being precise about what record is actually being broken here. There are tunnels elsewhere in the world that go deeper underground overall, mountain tunnels bored through solid rock far from any body of water, where the challenges are different because there's no equivalent hydrostatic pressure pushing in from every direction. What makes the Yangtze River estuary tunnel unique is the specific combination of extreme underwater depth, the presence of a high-speed rail line running through it, and the enormous diameter needed to accommodate that kind of train traffic safely. Compared to previous benchmark projects like the Bosphorus tunnels in Istanbul, this project pushes roughly 50% deeper than the previous deepest comparable underwater rail tunnel. That is not an incremental improvement. In tunnel engineering, where every additional meter of depth multiplies the pressure-related engineering challenges, a jump of that size represents a genuine leap rather than a routine upgrade. It is the kind of result that tunnel engineers in other countries are already studying closely, because the techniques developed here, the pressure-resistant sealing systems, the remote maintenance robotics, are not tied exclusively to this one location. They are transferable tools that could unlock deeper underwater construction projects anywhere in the world. Completing this section of tunnel is a massive milestone, but it is not the same as the project being finished. The full Shenzhen Jiangmen high-speed rail line still requires extensive additional construction, testing, and safety certification before trains can actually run through it, carrying passengers. Every meter of track and every system inside the tunnel, ventilation, emergency evacuation routes, drainage, structural monitoring, needs to be tested and verified independently before regulators will approve the line for public use. There is also the broader question of maintenance over the tunnel's lifetime. A structure operating permanently at 11 atmospheres of external pressure needs long-term monitoring systems to track for any signs of stress, seepage, or material fatigue over years and decades of continuous operation, not just during construction. None of this diminishes what has already been achieved. It simply means the record-setting tunnel boring phase is the beginning of a much longer process before the project delivers on its promise of a 1-hour connection between Shenzhen and Jiangmen. Complex infrastructure projects like this typically take additional years between major construction milestones and full public operation. The 113-meter number is the headline, and it deserves to be, because it quietly rewrites what engineers previously treated as the practical limit for large-diameter underwater rail tunneling. But the detail that actually impresses me most is the remote tool changing system,
Because it solves the problem that has arguably held deep tunneling back more than pressure-resistant materials ever did, which is the danger to human workers. Depth records get attention. Systems that remove people from the most hazardous part of an operation tend to matter more in the long run, because they change what future engineers are willing to attempt next. This project also fits a broader pattern worth watching. China has been steadily pushing the boundaries of underwater and underground construction for over a decade, from immersed tube tunnels to record-setting bridges, and each project tends to feed directly into the next one's ambitions. Whether the next deep tunnel gets attempted in China, Japan, Norway, or anywhere else with a coastline and a need for faster connections, the techniques proven here are now part of the available toolkit. That's the quiet part of engineering breakthroughs. The record gets the headline. The transferable technique is what actually spreads.
So here's what I want to know. If underwater tunnels can now go 113 meters deep and stay safe, where do you think the next record gets set? And which coastline needs a tunnel like this the most? Drop your guess in the comments. And if you want more breakdowns of the engineering projects quietly redrawing the map of what's physically possible, subscribe, because this is not the last record that's going to fall this year.